Okay, let's go over the continuous math question over here. So in the first part, we're asked to solve the constraint optimization problem, argmin of xy, ln x plus ln y plus 1 over x plus 2 over y, where it has to follow this condition xy is equal to 1 for x greater than 0 and y greater than 0. And then you may assume that a minimum exists. So for part A, what I did is there's kind of two ways of going about this. I think this is the easier way in the correction. Basically, the idea is, okay, I take what my expression over here, right, that I'm trying to find the minimum of. And then I see that, okay, I have ln x plus ln y. So I can combine that using log rules to be ln xy. And I know that the condition is that xy is equal to 1, so I can take advantage of that and it's long 1, which is just 0, so it cancels out nicely. And then I can also use the same condition, and just say that y is equal to 1 over x. So hence I would just have 1 over x plus 2x. So that I'm left with a very easy equation that I can manipulate. So I just have g of x is equal to this thing over here. And I can just take g prime of x to be equal to 0 for some minimum, and I find that x squared is equal to 1 half. So x is either equal to positive or negative of 1 over square root 2. And I reject this negative 1 because I know x is greater than 0, as the condition says. And y would just be 1 over x, which would be square root 2. So hence I find that this would be like the um, value. And since it promises that I have a minimum, great, I'm done because it's only one answer. But if I do want to verify, I would just take the second derivative of g, and then it would be this for 1 over square root 2, g prime, like the second derivative is greater than 0, so it's a minimum. So that's how we can verify it. The original way that I did this question was that I did not spot that it was I can simplify it using the x equals y equals 1 over x condition. So instead I just used the Lagrangian method. But I did simplify it using the long part so that this part became 0. And then what I did was for Lagrangian, I have my original function over here, right? And that I minus lambda of my condition over here. My condition over here was xy equals 1. So that I just rearrange it so that it's xy minus 1 equals 0. So then the here over here would just be xy minus 1. So yeah, and then I just solve it that, and then I have this equation over here. Then I just did what I did usually do, take the Lagrangian partial derivative with respect to x and with respect to y. Obviously, this step was extraneous because that would just give me my initial condition. So yeah, this would just be my two things, my two equations. Awesome. And now I'm just going to substitute them into each one. Okay, and then I can say that, okay, yeah, I'm just finding what the thing is. I get to the same part as before. I get that this is the root. The other one is negative, so it can't work. So yeah, basically we get to the same step as before. But I'd say definitely the first method is better because it's much easier to be just in one dimension rather than have to deal with the Lagrangian. And then for part B, we have let A be a m times n matrix. Using the method of Lagrange multipliers, solve the constraint optimization problem. Argument of AX, where S is equal to um, X is greater than the distance of X is greater than 1 or equal to 1. Expressing your answer in terms of eigenvalues and eigenvectors of a particular matrix, you may assume that a minimum exists. Okay, so for part BI, what we do is the following. So we are asked to minimize this thing over here, and then our S is this condition. If we're trying to minimize this, then wouldn't matter if we just squared it because it was already positive, right? And then squaring it wouldn't change where the minimal solution would be. So changing it to this form would make it much easier because we can just rewrite it as a dot product, right? Of the dot product of AX times transpose AX. So then just rearrange the transpose part. We have XT, AT, AX. And then this scales basically with the magnitude of x. So we know that the minimum will occur on the boundary where x is equal to 1, where that is the minimum, right? So hence we have the Lagrangian x and lambda, and then we have x, this expression over here, our original expression, minus lambda of this would just be the x squared minus 1. And then I can do something is that I'm going to take the gradient with respect to x and set it to 0 as usual, right? So taking it respect to x, what I get is the matrix over here, xt, at, ax. That's basically, we can treat it as, since we know that um, the matrix ATA is symmetric, we can say that, okay, we're going to get 2 times of that, right? Times x. And then we know that, okay, we have minus lambda times the first part. The first part would be just treated as lambda x, right? So it's -2 times that. So -2 lambda x. And then the last part is just a constant, which would evaluate to 0. So then what we have is just at of ax is equal to lambda x. So this is just the, what is it called? We finally got it to a nice linear algebra form where we see that the stationary points x must be eigenvectors of the symmetric matrix ATA. And the Lagrange multiplier is the corresponding eigenvalue from this point. So yeah, we get this over here. We put it back into the original expression, right? So we just see that this part over here is this lambda x, and then we can just take lambda in the front, and we just would get lambda x squared. So then it would just be, since we assumed that x was at the boundary equal 1, hence it's lambda. So basically what we can say is to minimize the projective function, we can pick the eigenvector associated with the smallest eigenvalue. Yeah, and the major takeaway here would be the fact that, okay, basically squaring this kind of distance wouldn't change it. So the dot product would make it much easier in terms of taking the derivative, I mean the gradients and stuff. On top of that, I think just taking the gradient, making sure that for xt, at, ax, if it was just a normal matrix, it would have been something of the form xt mx. Then it would have been m plus mt times x, right? And then since it's symmetric, then m and mt is the same thing, so it's 2 times that. And it's the same argument over here, but with the identity matrix. So hence, it would just be 2 lambda x. So yeah, and then for part 2, we're asked, without using the method of Lagrange multipliers, solve the constraint optimization problem, argument of ax where s is equal to this, where now we're smaller than equal to 1. So the only thing that changed was just the condition, right? The constraint of the constraint. So before, if we were greater than or equal to 1, we know that, okay, we want to minimize it, so we're going to pick it to be on the boundary where that would be the optimal case. But now we can go smaller and there's kind of no hard limit on what we can go, or is there? It's actually just 0, right? Because if we think about it, if it was just the distance, then the distance would have meant that it has to be 0 or positive, right? So 0 would be the minimum case. And we'll just see if 0 works, then that would just be the minimum solution. If it doesn't work, then we can find some other methods of doing it. And in fact, over here, our calculation is very simple because 0 does actually work. We can see over here when we have, yeah, basically the idea is that it has to be greater than or equal to 0. So the minimum, if it exists at 0, would be 0. So then we're just going to solve it with x equals to a 0 vector with dimension d, dimension n, we are actually satisfied. The only kind of thing is that if A is full rank, the solution would be unique. Otherwise, it wouldn't. So, but it doesn't matter, no matter what we're going to be kind of um, at the minimum solution. So yeah, BII is finished. And then we're going to move on to part C. Part C is just basically going over sort of different methods and choosing which one is better suited. In part I will ask two methods for finding a local min of a univariate function, given that one exists, are interval bisection and golden section search. How would you select between them depending on convexity of f, ease of evaluating its derivative, complexity of finding initial bracket, and rate of convergence of these methods? Okay, so I kind of drew it out over here. So if f is convex, it's best to use A. Otherwise, it's you kind of have to go with B because A requires um, interval bisection requires convexity. And that if derivative is easy to calculate, then it's better to use A because we're going to be every time looking at the thing. Otherwise, it's just better to use B because we don't require. And then complexity of finding the initial bracket, I think, wait, where am I? Okay, I guess this is much more detailed. So yeah, this was basically interval bisection requires f to be strictly unimodal. So yeah, basically it's already convex, so it requires it to be convex. And derivative is continuous and it changes sign. So that's why if it's possible to calculate derivative and it's relatively easy, good idea. Otherwise, not a good idea. Requires initial bracket where df dx has opposite signs at the boundary. So yeah, we need to find that, and it's relatively difficult to do that. And it converges linearly, so it reduces the interval by a factor of 0.5 every time because we're having it every time. And golden section search, on the other hand, does not require the derivative, so it's better if it's hard to evaluate or not possible. And it requires initial bracket of 3 points where the middle point has a lower function value than the edges. I think that's relatively okay, easier than finding the boundaries that are different in signs. And it converges linearly, and it reduces interval by a factor of the golden ratio 0.618, which is slightly faster than the interval bisection method. So yeah, that's the difference between the two. And then for part two, we have two methods for finding a zero of vector field, FRD, are Newton's method and Broyden's method. I would select between them depending on the same kind of conditions, convexity, ease of evaluating Jacobian, dimension D, and rate of convergence. It's always kind of these conditions that we kind of consider, except earlier it was this kind of derivative, now it's Jacobian. But essentially, Newton's method does not need to be convex, but it's highly dependent on the initial guess and can do quite poorly in some non-convex regions. So it's a good idea to be convex, but it doesn't necessarily have to be one. But it does have to have the exact Jacobian each set, which means that if it's hard to calculate or difficult to calculate, yeah, for sure, not a good idea to use Newton. And for D dimension, it requires solving a D times D system. So the complexity of doing so would be O of D cubed. So if it's hard to solve that, if the dimension is large, not a good idea either. But definitely the advantage is its rate of convergence very fast. It's quadratic, especially near the root. It's very fast. On the other hand, we have the Broyden's method, which does not need to be convex and does slightly better than Newton's method when it is kind of weird. Um, it just approximates the Jacobian each step by updating the inverse Jacobian matrix in O of D squared. So hence, one is cubed, one is squared. Obviously, for high dimension, it's better to use Broyden's method. And the only kind of trade-off is that it's kind of super linear convergence because it's not exact, right? So I'd say um you it's if it's hard to calculate Jacobian, for sure use Broyden's. Part three, we're asked to find two methods for a local min of a multivariate function are gradient descent and BFGS. I would just select between them depending on convexity of f, ease of evaluating Hessian dimension rate of convergence. So the difference between those two are the fact that gradient descent is more prone to oscillations in ill-conditioned convex problem and non-convex problems. And it does not require the explicit evaluation of the Hessian. It only uses the first order gradient. And the complexity for it is O of D, and it converges linearly. BFGS does relatively better in ill-conditioned convex and non-convex functions with line search and truss regions methods. And it does not require explicit evaluation of Hessian either, but it does build inverse approximation of it. For the Hessian approximation, it takes O of D squared, right, to evaluate and to keep, and it converges superlinearly, which is slightly faster, but if it's hard to kind of even approximate the Hessian, keep track of it, if it's large, not a good idea to use BFGS either. So yeah, that ends off basically this problem set. I kind of wanted just to go over some of the first is kind of the solution in the front. There's some kind of mistakes in this, but I'm just recording this video for myself so that I can look over what my thing is rather than have to search out what my solutions are, which would be a pain. So yeah, this would be my answer key that I did originally. And over here are just some sort of notes that I kept for comparing what the sort of different algos are for finding stuff. So the first one is interval bisection. Um, Basically, the idea behind this is that we find a left side and like the boundary case where the signs are different. So then every time we're just doing binary search on it. If it's the left, then we change the left. If it's the right, then the right. And we just shrink that interval by, every time by half and just making sure that we can always find that root. I guess the advantage is that it's guaranteed to converge because it's continuous and we know that the root has to be within the thing. It's easy to implement, it's derivative free, so it's pretty nice. But the disadvantage is that it can be slow to other methods. Um, Sometimes it can't find the touching roots, which basically means that, for instance, in the case that like something was just tangent to the thing, but it doesn't cross, so it doesn't change signs, we can't find it. And it requires a bracket, which might be hard to find if we don't know the behavior of the function. The rate of convergence we talked about is linear with the rate as 0.5. So yeah, this is kind of the rules to go through it and an example of the iterations. I'm not going to talk too much about it. But yeah, and there might be some issues with kind of like the rounding epsilon. But yeah, not so much to talk about. That's just the main idea, I say. And the golden section search is basically a pretty smart way of taking advantage of the tertiary search. Basically, the idea that binary search earlier, we kind of just divided the interval into halves, right? For tertiary, what we do is we divide it into thirds. But in DAA, we already proved that, like the idea that using thirds of just exactly 1/3 of the length is not as good as the binary search, mainly because we have to do more evaluation and this is more cases in general, which doesn't actually lead to efficiency. So instead, what the golden search takes advantage of is the fact that, okay, it just considers I'm going to split off this such that it's not exactly 1/3. This is actually just the interval 0.618, the golden ratio. This section is that ratio of it, and this one is that ratio as well. So that if I pick whichever boundary I pick, this would be now the next kind of mark for it. So then that means that basically we only have to do one more evaluation over here to actually know the boundary rather than have to do two more. Because if we were in the thirds, then it would have been if we were to pick somewhere over here, this would have been awkwardly placed in the middle. So that means that we still have to evaluate two more, which doesn't help in our case. Whereas the golden section search takes advantage of the fact that, okay, I already evaluated this point, so I don't need to evaluate it again. So I'm just going to evaluate one more point and I can just be more efficient with that, even though I'm going to trade off maybe slightly less each time. Not 1/3. I don't cover 1/3, but slightly less. But still, that makes me have to evaluate one less point than that. But some of the preconditions that have to be true is that f of x has to be strictly unimodal over the interval. That means that there must be only one local min or max in that range, and it basically has to strictly decrease or increase to kind of reach that. And yeah, you have to have the valid bracket. And it's relatively efficient, it's nice, 0.618 linear convergence, so it's pretty nice. So these are the rules, explicit rules, worked examples. Yeah, this is basically why the golden ratio, I think I already explained it. Basically, the idea is that the tertiary search part, yeah, and this would be kind of the proof that why do we do that? Basically, we're cycling it. So we have to calculate one less value than before. Okay, so that covers golden section search. And then the third thing that we go over is Newton's method, which is used quite a lot. I'd say it's a nice algo and very, very efficient for finding the thing, although it's kind of only works pretty well when you're really close to the answer, when like your initial guess is close to the actual value, will actually work out pretty well. And it has to be relatively in a nice function to work. If it's like a very weird function, then it might kind of diverge off because essentially what we're doing for Newton's method is that we're just drawing a tangent line at whatever point where our initial guess is, and then we're going to just approximate it by a certain amount. And then in the next step size, we're going to repeat that process again, and then we're just going to draw a line and hopefully get closer to the approximation. So yeah, that would be Newton's method. Basically, it requires differentiability. We need it to be continuous and differentiable. Non-zero derivative because we're taking what is it called? A tangent, right? And then you need to have a good initial guess. That has to be like a 100%. If it's kind of initially off by quite a lot, then your approximation can be quite off in kind of retrospect, like in chain effect. And then advantage is that it's kind of fast and self-correcting. Disadvantages is that it could diverge, especially in the case that the initial guess is bad, then the function has inflection points or other things that are weird, and it can shoot off to infinity or do something weird that you don't expect. And yeah, you do need the derivatives. And in high dimensions, unfortunately, you need to calculate like the Jacobian, which is not fun if it's a hard function. But the good part is that it's quadratic, but very fast. And then this is sort of like the function update formula. X of n plus 1 is equal to xn minus f of xn divided by f prime of xn. So that's the formula for it. And if it's kind of multi-dimension, it would just be x of n plus 1 equals xn minus Jacobian, inverse of the Jacobian of f of xn. So yeah, basically this would be very computationally expensive because, yeah, inverting this takes this amount of time, which is not good. And there's kind of two formulas for it. For root finding, we have this formula over here that we just saw. And then for multi-dimensional optimization, which I barely ever see because Newton's methods is not it for multi-dimension. And so this equation over here. And then the next one is talking about what is the next algo? Broyden's method. It's a quasi-Newton method for finding nonlinear equations. It's basically, you can think of it as like an extension of the secant method. It's like the more general version. What it does is kind of avoids having to calculate the exact, and then it's instead kind of just builds like an approximation as it goes along. So yeah, we have this, you have an initial guess, what you have, and then you don't have to calculate the exact, so it's just OD squared rather than D cubed from earlier. But it is kind of slow because you do have to It is an approximation rather than exact, and it's still memory heavy, but it's obviously better than the one before. And yeah, initial guess is also quite dependent. Superlinear, um, this is sort of the approach over here. So like it would just kind of do like that. And here it's just basically saying, okay, Boydens versus BFGS. So Boydens is for root finding, and then BFGS is usually for optimization, for finding the minimum. And then this leads us to gradient descent. And then gradient descent is to find local min. Then basically we just kind of finds the gradient, and then we're just going to point it to the more local minimum point. And then we're just going to go down, down, down like that. And how this works is that, okay, we do need it to be differentiable, so first order, but doesn't need the second order. And then we do need an initial guess, as most things require. This one is really efficient because it only takes the first derivative, scalable, and it's relatively easy to implement. But it could do poorly in places where it's really random and weird. The functions are weird, right? Because it's not really smart, doesn't take account of those things. So for instance, in saddle points or local min or local shallow ones, it could miss the deeper global ones. It could also zigzag in like the ill-conditioned cases where the convex shape is like really weird and it just takes the gradient of that point, but that point could vary a lot, right? So it could just oscillate back and forth. So yeah, it's linear convergence. Guess it's all right. So this is sort of the function and an example of it. Um, and then the last one to go over is the BFGS. It's also the same method as talked about earlier, quasi-Newton for optimization. Basically, the idea is that this one kind of just uses a lot of different kind of approaches and then just takes like the more optimal of each one, I'd say. Like some of the preconditions it requires is that it does require second derivative to exist, does need the differentiability part, does have to do line search, and have initial guess, the Hessian, inverse Hessian. So we don't necessarily need the second derivative, but we do build it up. And guess it does do much better in terms of like weird shapes because it can navigate the steps because it corrects for it. And then this is kind of the main thing is that it's positive definite like throughout, so it's pretty nice that it will point you downwards. Um, but the cost of this would be you do have to store more d times d, and then it's relatively harder because there's more things to consider. But the benefit of that is having a superlinear convergence, and this would be like the algo to do it. So yeah, I think that brings us to mainly the end of this question. I think it's a really long one, but I will definitely go into more depth of each of these algos in the notes section. This is just like a brief overview before I dive into it in next week.